Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of particle physics with the course code PHY 452, we are at the lecture number 28 and the topic is the Dirac equation. We have seen in our previous lecture the Klein-Gordon equation. In Klein-Gordon equation, we have derived it from the Schrodinger equation. We had the time derivative and the space derivative on equal footing, that is square of them. Because in quantum mechanics is a non-relativistic mechanics and the Schrodinger equation is manifestly non-relativistic, where the special theory of relativity introduced by Einstein in 1905 demands that every other theory of physics must obey it. That is, it must be a relativistic theory. And since quantum mechanics is a non-relativistic equation, it does not obey special theory of relativity. Then there was a demand, or there was a need to derive an equation which is relativistic as well as quantum mechanical. Klein and Gordon attempted to derive such equation, and but they only succeeded with the Klein-Gordon equation, which had some problems. For example, first of the problem was that it does not conserve probability, and so in principle it is not a quantum mechanical equation, because quantum mechanics requires that the probability must be conserved. And the second is that it deals only the spin zero particles or spinless particles, and it cannot describe the particles of spin half such as electron. Because of these shortcomings, Dirac thought that there should be a proper equation, another equation which resolves these problems. So in today's lecture, we will see that how Dirac equation resolves these problems, and we will also derive the Dirac equation and will study its different properties. So let's start and revisit the Schrodinger equation and to see that why the Schrodinger equation is a non-relativistic equation. The time-dependent Schrodinger equation is not symmetric in space and time derivatives and hence not relativistic. So if you look at the Schrodinger equation, this is the Schrodinger equation, and on the left side we have the term I h bar del by del t psi, where psi is the wave function which is a function of position and time. You can see over here that the energy derivative is first order. That means that there is only one derivative and its power is 1. But on the other hand, if you see on the left hand side, there is a Hamiltonian acting on the wave function, and this Hamiltonian is equal to p square by 2m in the case of the free particle. And we see that it is already a second order derivative involved in the Hamiltonian, which is p. And p is the momentum operator. And if you write this p, this is equal to minus I h bar del by del x, del by del y, and del by del z. So you see, if I put this p into p square, there will be a square of the derivatives of all these space derivatives. So it means that the Schrodinger equation is not symmetric in time and space derivatives, and hence it is not relativistic, because special theory of relativity demands that time and space must be treated on equal footings. And since in in the Schrodinger equation, time and space are not treated on the same footings, we see that the single derivative with respect to time, but we see the double derivative or quadratic derivative, second order derivative with respect to space. So this is manifestly a non-relativistic equation, and hence the quantum mechanics generated or created from Schrodinger equation would be a non-relativistic quantum mechanics. And since there was a demand from special theory of relativity which cannot be denied, that every theory should be relativistic. So Dirac and Klein-Gordon and Dirac faced the problem to make this equation relativistic. So now we see that how Dirac went about it and derived another equation which was relativistic. So Dirac proposed that we can have a Hamiltonian which is linear in space derivatives as well. So it is linear in time derivatives, but we can have a derivative, a Hamiltonian which is linear in space derivatives. So Dirac introduced the Hamiltonian that is linear in space derivatives, and this one, where h you can see is equal to c alpha dot p and beta mc square. In this Hamiltonian, you see that p is appearing over here, and p is not quadratic. It is not coming with a square, but it is coming with the first order space derivative. So it removed the problem of having double derivatives. Okay, so this is now linear in space derivative and does not involve time. And then what he did that before that, these alpha and betas, these parameters alpha and betas are dimensionless parameters to be determined later on. We will see that these will turn out to be matrices, but at the moment you can just treat them some dimensionless parameters to which we will determine later. But this was the Hamiltonian suggested by the Dirac to replace the Hamiltonian of the Schrodinger equation, so that to make it linear in space derivatives as well. And when we substitute this Dirac Hamiltonian into the Schrodinger equation, as you can see over here, the Schrodinger equation had the energy term. This energy was there in form of the time derivative, that is minus I h bar del by del t, but it has a linear time derivative. But now this Hamiltonian coming over here, which is linear in space derivatives as well, as you can see, minus c alpha dot p plus beta mc square psi r of t. Now this equation, this resulting equation, is not quadratic in any derivatives, not in the space derivatives and not even in the time derivative. So we make the following substitutions again. If we replace E with minus I h bar del by del t, and we replace P with minus I h bar del by del x, so E with I h bar del by del t, so you see now E is entering with the one derivative and P is entering with the one derivative, and there is no square involved. So we have resolved, or the Dirac resolved, the problem of an equation which is not relativistic, which was treating space and time derivatives space and time differently. And now it is not treating it differently, but they are on equal footing. So this equation is now a relativistic equation. So if you put these or substitute and replace this E and P with these derivatives, what you will get is I h bar del by del t, I h bar c alpha dot del, and this del is because of the other derivatives with respect to y and z components also involved, and minus beta mc square psi of rt. So this equation is a Dirac equation. We call it a Dirac equation, and you can see now here that we have two things to be determined, that is one alpha and beta, and the rest is clear. So structure of alpha beta, we want to know now what is the structure of these alpha beta. For this thing, we multiply the following equation with the this equation, that is E minus C alpha dot without putting in the derivatives for E and P, with this term. That is, here is a minus sign, so we get the plus sign over here, and we multiply this equation, this above equation, with this the equation downstairs. We multiply these two equations in order to find out what is alpha and beta. If we do this, what we obtain this lengthier equation, and you can check out this, that it is really coming from this. So first term will be multiplied with the first term, giving us the E square, and the second term will be multiplied with the second term, so it will give us C square over here minus, and then we will have, because these are the two vectors alpha and dot p, this is the dot product of alpha and p, So we will get x component of them, that is alpha x square px square, and then we get px square multiplied with this, and then we get y the component, alpha y square py square, the z component, and then what we will get the mixed components. For example, so this is three dimensional, so we have alpha x, alpha y, alpha z, and px, py, pz. So first alpha x multiplied with alpha x, alpha y with alpha y, alpha z with alpha z, but now alpha x with the alpha y. So this here term you can see alpha x with the alpha y and alpha y with the alpha x, and since these both involve px and py, which is a common. And then similarly y and z term over here, and py, pz is taken common, and again similarly z and x term and pz and px common. And then we have the product of these two terms, that is beta square minus beta m square c square beta square, this and then we will have the other terms when we get multiplied coming from alpha multiplied with beta. So we will get minus mc cube, and because this multiplied with this and this cross terms, we get mc cube alpha x beta plus beta alpha x in px component, and then n py component and the pz component. So this is all. So we have seen that by having this, and we shall actually having a minus sign over here. So by having multiplied this equation with that equation, we got this complicated term over here, and this is equal to 0 as on the right side. Okay, and this equation, this lengthier equation, will now help us to determine the structure of alpha and beta. So this equation reduces to Klein-Gordon equation if we do this. For example, if we put alpha x square, alpha y square, and alpha z square, and beta square is equal to identity, and alpha x and alpha y commutator, because anti-commutator, because you see over here in this equation that this alpha x, alpha y, alpha x is actually an anti-commutator. What is anti-commutator? If we have two operators, for example a and b, and we calculate their anti-commutator, sometimes we also write it with the curly brackets or braces, or sometimes with a plus sign outside the square bracket like this, and the calculation is this, that AB plus BA. We know the commutator is equal to 0. We know the commutator is actually A comma B is equal to AB minus BA, but in this is the commutator, and this one is the anti-commutator coming with a plus sign. So you see that all these terms over here are anti-commutators. So so this equation this equation over here reduces to the anti-commutator if reduces to the Klein-Gordon equation if we put the square of the alpha components terms equal to identity, and we also put these anti-commutators of alpha x, alpha y, and yz and zx equal to 0, and also the anti-commutators of alpha with beta. So if we demand that these commutators are 0, or in other words we say that alpha beta commutes, all of their components commutes, and when you square them they reduces to identity, what you get is where I denotes the 4x4 identity matrix, and all of them are 4x4 identity matrices, because if these conditions are only obeyed by the 4x4 matrices, and if you do it in the lower dimensions you will not see that these requirements are obeyed. So and here is the definition of the anti-commutator, as I have already said, that the anti-commutator of AB is equal to AB plus BA, where the commutator comes with a minus sign, denotes the anti-commutator. Okay, so if you substitute this for example in here, so what will happen, this will be equal to 1. So what we will get E square minus C square px square py square pz square, and since this is 0, all these terms, the rest of the terms will go away except this term which will be equal to identity, and we get exactly the Klein-Gordon equation. So in this limit we get the Klein-Gordon equation, and as these operators appear in the Dirac equation, it follows that the Dirac wave function must likewise be four-dimensional. As I said, these are actually matrices, and these matrices are four-dimensional matrices. And since these are matrices and they are in Dirac equation, and these matrices with the help of operators will act on the wave function, so wave functions also in Dirac equation have to be four-dimensional. So choosing beta as a diagonal matrix, for example, if we choose beta to be this one, and where I is the identity matrix, and where I is a 2 cross 2 identity matrix, but when we put it over here, then identity, so this beta becomes a four-dimensional identity matrix, diagonal, which is diagonal 1. Okay, and the alphas are these matrices, and alpha is made of the polyspin matrices. The sigmas are actually the polyspin matrices, very famous matrices introduced by the Pauli: sigma x, sigma y, sigma y, sigma y over here, and sigma z, sigma z. But what are sigma x? And they are more concisely then written as beta is equal to I minus I, and alpha is equal to 0, 0, and sigma, sigma. And these sigmas are polyspin matrices, and they have values in terms of iota and ones, and they are 2 cross 2 matrices. So when we put them here in the alpha matrices, which are 2 cross 2, they convert them into a 4 cross 4 matrix. Okay, so after explaining the matrices, these are sometimes also called the gamma matrices. They are very famous, popular matrices with the name gamma Dirac gamma matrices. Here we denoted it with the alpha and beta, but they are also known as gamma matrices. So polyspin matrices, as the alpha matrices are composed of polyspin operators, they obey the commutation relations, like alpha x alpha y is equal to 2 iota alpha z. So if you check this for the these matrices, you will find out that they obey these relations. Okay, next we turn to deriving the density and current expressions, the charge density and the current expressions. And you know that a continuity equation may be obtained from the Dirac equation, and this is done, as you know, that multiplying a Dirac equation with the psi dagger, which is the complex conjugate or adjoint, not exactly complex conjugate, but the adjoint equation. So del by del t psi dagger psi, this psi dagger is the adjoint of psi, and del dot c psi dagger alpha psi. So if we multiply these equation, so if we multiply Dirac equation with a psi dagger from the left, and then we write the adjoint equation and multiply with the psi, and then we subtract these two equations, we will get this equation. And from there you can see the first term over here. This first term is giving us the current density, and the second term is giving us the first term is giving us the charge density, and the second term is giving us the current density. So this is the rho, which is the as you can see is the charge density, that is psi dagger psi, and the second term j, which is the current density, and this is c psi dagger alpha psi. And now this probability is also conserved, or this charge density is also conserved, and current. So altogether they obey the continuity equation, and we see the problem of the probability conservation is gone, and we see now that the Dirac equation is a quantum mechanical equation, and it conserves probability. So after this we turn towards the solutions of the Dirac equation, because these are very important. They give us some physical insight. So solutions are that in the plane wave solutions, we will derive the plane wave solutions to the solution to the free particle Dirac equation. So this is the plane wave solution, where you can see this is a plane wave, e raised to power kx, k dot r omega t, and a is some coefficient, where E is h bar omega, the energy. We can put we have put E is equal to h bar, and P is equal to h bar k. So these are the two substitutions. If we do, then this is the plane wave solution to the Dirac equation, where A is a 4 component column vector, where the components goes from j is equal to 1 to 4. Okay, then what we do that what we get is the algebraic equations for a dagger a bar, and these are the terms coming from the Dirac equation. These are the 4 sets of equations. As you can see, these equations have a non-trivial solution only if the determinant of the coefficient matrix vanishes. So their results as e square minus m square c4 minus c square p square whole square is equal to 0. So what we are getting now is the spin up and spin down solutions, as in here you see for this equation, which because there was a square root, there was a square in here, and if you remove the square you get 2 solutions, that is e plus solution and a e minus solution, and this is with a plus sign and this is with a minus sign, where psi plus and psi, this is the psi up plus sign and this is psi down plus sign, and this psi minus and psi down, with the definition delta plus minus is equal to this. So it means that in Dirac theory we have not only electrons but we also have positrons. The similar thing was there in Klein-Gordon equation as well, because it predicted the negative energy solutions, and because of these negative energy solutions Schrodinger did not publish this equation, although he derived it before the Klein-Gordon. And the same thing appeared in the Dirac equation as well, that we had the negative energy solutions. So in the beginning Dirac proposed an idea of Dirac C in order to explain these negative energy solutions, where he said that that we are living in the sea of electrons, and whenever one of the electron is missing there, it appears as a positive energy solution. But later on, with the discovery of positron, it was understood that these positive energy solutions are actually independent particles, antiparticles, positron. And later we know that now every particle should have the antiparticle. So this was actually discovered by mixing the quantum mechanics with the special theory of relativity and getting these positive energy solutions, which initially was thought to be a problem, but later on it led to the discovery of antimatter. Okay, so now relation to the electron spin. So it follows that in this non-relativistic limit one may write the solution, as you can see, psi plus up and psi down. So it predicts also that there is a psi, 2 types of electron, up and down, and this is 1 0 and 0 1 representation. We have written this psi in terms of the plane waves, and you can see that there is energy gap of it 2 mc square 1 mev energy gap, and from there we see that we have 2 solutions. One is a positive energy solution and another is a negative energy solution corresponding to the antiparticle called positron. So electrons and positrons. So thus the energy spectrum of free particle in the Dirac theory is continuous and ranges from minus infinity to plus infinity, except for the forbidden gap of it 2 mc square 1.02 MeV. And these are now the 2 solutions, as you can see, the E plus and E minus, that is the positive energy solution and the negative energy solution. So positive energy solution corresponds to 1 particle, there may be electron, and the negative energy solution to the positron or the antiparticle. So in this way, in today's lecture we have seen that how the Dirac equation was derived, and how it combined the quantum mechanics with a special theory of relativity, and it removed the problems of Klein-Gordon equation, that is, it was only defined for spinless particles, but now Dirac equation is defined for also the spin half particles like electrons. So it is more practical and a realistic equation. And on the other hand, it also removed the problem of quadratic derivatives, and it has also removed the problem of conservation of probability. It conserves probability as well, and it also predicted the antimatter, that is for electron another particle positron, which was later discovered in 1932 by Anderson. So this was a very successful theory, like a successful equation, a celebrity equation, and later on it has been applied in many practical situations and have provided meaningful insights into quantum relativistic quantum mechanics. With this, I say thank you to all of you.